Hello everyone. Today, we will study the content of the printing process control. First, let's look at the solid density. The objective evaluation of the printing process focuses on measuring the physical properties of printed products through detection tools, that is, the commonly used spectrophotometer, combined with printing quality standards. The physical properties of printed products are quantitatively detected. Then, through mathematical statistics and necessary comprehensive analysis, conclusions are drawn. The process evaluation of the color quality of printed products uses statistical methods to calculate the results of subjective evaluation, and then converts them into corresponding physical quantities, which are used as objective evaluation standards. In this way, the influence of human factors in the evaluation can be eliminated. With a standardized and unified standard, the color quality of various printed products can be fairly evaluated. And finally, it can be made to better conform to the subjective evaluation standards of most people. The objective evaluation method mainly uses specific measuring instruments and tools, and measures some standard elements printed together with the printed product image. That is what we mentioned before about measuring densitometers and the like. Only through measurement can the automatic control of printing quality become possible to a certain extent. To keep the printing color stable throughout the printing process mainly depends on three factors, which are what we usually call the ink film thickness, dot size, and ink over printing rate. First, let's take a look at the solid density. In printing, we usually use the letter DS to represent the solid density. The subscript S represents the solid area, which is the first letter of the abbreviation of the English word solid. It is also called the solid reflection density. From the graph, we can see the relationship between the ink film thickness and density. The visual color of the printed image depends to a certain extent on the thickness of the printed ink film. For coated paper, an ink film thickness between 0.7 and 1.1 microns can achieve the correct color position. Here we are referring to offset printing. According to the situation of the substrate and ink used, the maximum ink film thickness in offset printing can generally reach 2.5 microns, and usually we use about 1 micron. For transparent primary colors, in the change of the ink film thickness, the photochemistry will cause a change in the color saturation of the color, and the brightness of the ink film will also be affected. As a result, it will deviate from the specified color position, thus causing color changes in the printing process. In addition, it also limits the range of colors that can be reproduced. The visual inspection of the ink film thickness or ink film density only has a partial effect and is inappropriate. However, because the required precision is relatively high when used in the printing workshop, including daily work, measuring the actual ink film thickness value is inappropriate. Therefore, the densitometer has become the main measuring instrument used for quality inspection and control in the printing workshop. Of course, it does not necessarily only include the densitometer. The spectrophotometer can also be used for density measurement, so that it can detect and control the differences in the ink film thickness. If the saturation of one or more primary colors, that is, the ink film thickness we mentioned, is lower than the optimal value, then the range of reproduced colors will be slightly reduced. For density measurement, a reflection densitometer that meets the ISO requirements is usually used. Because most printed products are reflective, before using the color reflection densitometer, it must be zeroed and calibrated according to the instruction manual. A standard whiteboard is used. The substrate with the control strip should be placed on a flat platform. When the substrate is a single-sided printed product, a standard white color should be used as the substrate. When measuring, the measuring head of the densitometer should be closely attached to the control block to reduce measurement errors. When measuring the solid color patches, we know that for the primary color patches, intermediate color patches, or complex color patches, we can obtain the reflection densities of the solid color patches of the red, green, and blue color filters. In this way, we can obtain a set, 3, of density values, corresponding to the 3 color filters of red, green, and blue. Usually, DH is the high density, DM is the medium density, and DL is the low density, that is, the smallest density value. Take DH as the main density of the solid color patch, that is, DH is the solid density. For example, for a certain primary color ink, that is, the solid patch of yellow ink. When using the red, green, and blue color filters, to measure its density values, which are 1.0, 0.06, and 0.11 respectively. At this time, we use the density value DH of the color filter corresponding to the complementary color of the yellow ink, that is, the blue color filter, as the solid density of the yellow ink. The DH value of the solid area is also the main density of the primary color ink. And the other 2 density values, DM and DL, are the densities that the yellow ink should not have. This is because the inks in practice are not ideal, because the 3 primary color inks actually used cannot be ideal inks for a certain spot color solid patch. If a set of 3 density values measured by using the red, green, and blue color filters are DH 1.51, DL 0.21, and DM 1.43 respectively. Take DH as the solid density of the spot color solid patch, which is represented by DS, and it is also called the density value controlled during the spot color printing. For the solid patch of black ink, use the special color filter of the color densitometer to measure its density value, which is the solid density value DS of the solid patch of the black ink. The definition of the solid density DS is the logarithm, with base 10 of the reciprocal of the reflectance rho, which we call the reflection density. The measured area has a 100% dot coverage rate, that is, what we call the solid area, and its corresponding reflection density. The maximum value is called the solid reflection density DS. The value of the solid density dV is measured after the control strip. The screen density of the halftone is usually represented by dt, and the subscript T represents that it is also measured on the control strip. The larger the ratio of the dot area to the total area of the measured area, and the thicker the ink film thickness of the given ink, the larger the measured screen density of the halftone will be. In the formula, IO represents the incident light quantity, IF represents the reflected light quantity, LO is the incident light intensity, and LF is the reflected light intensity. The reflectance can be calculated from such a ratio. There is a close relationship between the ink film thickness and the ink film density. The absorption characteristics of the ink film mainly depend on the hue, ink film thickness, and the nature and concentration of the ink pigment. However, since the hues of some primary colors are already fixed, and the pigment concentrations of these primary colors are also regarded as being within a certain range, only the ink film thickness is the parameter that can be changed by the printing operator. From the graph, we can see the following relationship. Low ink amount corresponds to low ink film thickness, corresponding to light hue. Low absorptivity, high reflectance, and low density value. High ink amount corresponds to high ink film thickness, full hue. High absorptivity, and finally low reflectance and high density value. That is to say, the lower the ink amount, the lower the density value, and the higher the ink amount, the higher the corresponding density value. When the ink film thickness increases to a certain thickness, if the ink film thickness is further increased, it is difficult for the ink film density to increase again. At this time, the maximum density is reached. Printing inks will always reflect a certain amount of light, so there will be no infinite density value. When the tinting strength of the ink is constant, the solid density value ds can indirectly represent the ink film thickness of the color ink. The position of the vertical dotted line in the graph at a position of 1 micron is the commonly used ink film thickness value in offset printing. The initial actual density ds increases with the increase of the ink film thickness. But then the increment of the solid density gradually becomes smaller than the increment of the ink film thickness delta. When the ink film thickness reaches a certain value, that is, ds reaches the saturated density value D max, which is what we call the saturated solid density. At this time, if the ink film thickness is further increased, the ds value of the actual density will no longer change. So the ink film thickness has nothing to do with printing, since in the actual printing process, the tinting strength and proportion of each color ink are already clear. Controlling the solid density of each color ink means controlling the thickness delta of the ink film of each color impression. The difference between the wet and dry densities of the ink film of the impression. What we need to pay attention to in this part of the content is that the inks used in this table are medium yellow, peach red, sky blue, and black. The phenomenon that the wet color density is greater than the dry color density is what we call the dryback density, that is, the dryback density difference. The reason for the occurrence of the dryback phenomenon needs to be explained from the change of the surface reflection of the ink film of the impression when it is in the wet and dry states. In this graph, we can see that the ink film of the impression just printed on the paper surface is in a wet state and has a certain degree of leveling property. So the surface reflection is mainly specular reflection. Visually, it is manifested as bright color, good luster, and dark ink color. When the ink film of the impression is in a dry state, the surface reflected light is mainly diffuse reflection, and the color luster is lighter than that when it was just printed, and it appears dull. This phenomenon is more obvious on paper with strong absorbency when measured with a color reflection densitometer. As we can see from the graph, the receiver receives the reflected light flux from the surface of the ink film. That is, in the 0-degree direction, the wet color is significantly less than the dry color, since the reflection density is the logarithm of the incident light flux divided by the reflected light flux. The wet color density is greater than the dry color density. That is to say, the density of the wet ink film is higher than that of the dry ink film. Since the dry color density generally can only be measured 30 minutes after printing, this brings certain difficulties and limitations to the measurement and control of the printing quality on the printing site. Therefore, when measuring the printing density, we need to consider the influence of the dryback density. Generally speaking, for the commonly used inks nowadays, the dryback difference of black is generally in the range of 0.05 to 0.1. The dryback density difference of magenta and cyan is about 0.02. And the dryback density of yellow is relatively small, only 0.01. Or even there is almost no change, as we can see from this graph, because most of the measurement conditions are 45 degrees and 0 degrees for detection. From this comparison, we can find that the reflected light fluxes of wet and dry are different. Mainly this difference. To solve this problem, a color reflection densitometer with a polarizer can better solve the above problems. As shown in the figure, the light emitted by the light source is unpolarized light, which is a random combination of countless linearly polarized lights, and does not exhibit a polarized property. At the position B in this figure, after passing through the polarizer C, it becomes a linearly polarized light in a single direction, that is, linearly polarized light. When this linearly polarized light is incident on the ink film of the impression, it is divided into two parts. One part is reflected from the surface of the ink film as D, and this part of the light still maintains the original linearly polarized state. The other part passes through the ink film E and is then reflected back by the paper surface. After the selective absorption of the ink film, it is finally reflected by the paper surface. But this beam of light has been depolarized and restored to unpolarized light. Since the polarization angle of the polarizer G and the polarizer C differ by exactly 90 degrees, the polarized light D, directly reflected from the surface of the ink film, is exactly blocked completely by the polarizer GAND, cannot pass through. However, the unpolarized light F, reflected from the paper surface through the ink film E, can partially pass through the polarizer G, and is received by the receiver H with a color filter, and then converted into the corresponding density value. This type of color reflection densitometer eliminates the influence of the light reflected from the surface of the ink film. The measured wet color density and dry color density are quite close, and there is basically no difference. The measured density value is not affected by the wet and dry states of the ink film. Therefore, it has the advantages of strong comparability and high precision. This is the commonly used measurement mode M3 in density measurement. Therefore, we should choose a color reflection densitometer with a polarizer device, and the brand and model must be the same, to eliminate the influence of differences such as color filters, polarizers, and light sources. In short, to make the printing quality data-based, standardized, and normalized, the specified density values need to be controlled. The calibration of the density value ds is based on the principle that the solid density ds of a certain color corresponds to the maximum relative contrast Cmax of that color. That is, the ds value corresponding to Cmax is the commonly used calibration value of ds. This is to determine the maximum solid density according to the relative contrast. The specific steps are as follows. Under the condition of reasonable properties of the packing and appropriate distribution of the ideal pressure, the same substrate is used. The ink feeding amount of the ink fountain of the printing press gradually increases from small, but the axial ink amount should be uniform. That is, the lateral ink amount or the ink amount on the left and right should be uniform. In order to make the ink film thickness of the printing plate with the control strip uniform, the ink-water balance during printing should be good. Under the above printing conditions, a certain number of sheets of paper are printed to make the printing ink color stable. When the ink film of the impression reaches a certain thickness, the relative contrast value K reaches a maximum value, Cmax, as shown in the figure. The corresponding ds value is the calibration value of the solid reflection density of this color, according to the quality grade requirements of the printed products. Determine the upper and lower ranges of the calibrated ds value. The significance of the actual density calibration is mainly to enable the printing to proceed smoothly, without occurrence of backside smudging, or the situation where the color does not meet the requirements. Under the condition that the tinting strength of the printing ink is determined, the measurement and control of ds is to control the solid ink film thickness and the uniformity of the ink film, and to make the relative contrast, dot gain, etc. in the measurement, and control items within the specified tolerance range. Therefore, the measurement, control, and calibration of ds are the basis for the objective evaluation of printing quality. The standard data of the solid reflection density ds varies due to the differences in printing inks, substrates, and other conditions. The calibration values of ds when each color ink is printed cannot be generalized. It must be determined through the relationship between ds-Cmax. Under the premise of clarifying the printing conditions, only the ds value that matches it is meaningful. Generally, the control range of the solid density ds values of the 4 color inks of high-quality printed products is that cyan is generally 1.45 plus or minus 0.5, magenta is 1.35 plus or minus 0.05, yellow is 1.05 plus or minus 0.05, and black is generally 1.75 plus or minus 0.1. It should be noted that the so-called density values here are corresponding absolute density values. That is, relative to the standard whiteboard. The standard ink coverage is the solid density that can enable a specific substrate and ink to obtain the best printing effect. To determine the reference ink film density using color samples, it is necessary to determine the standard ink coverage. To better determine the printing press and select inks, blankets, etc. for various primary colors, that is, the 3 primary colors or the 4 primary colors. The solid areas under the standard ink film density must be consistent with the corresponding standard demonstration samples specified in the optical standards. When determining the standard ink coverage, a rubbing density gradient from obvious insufficient ink coverage to obvious excessive ink coverage is used for determination. This concludes today's lesson.